Hi guys, it's Joe here. In this video, we're going to be looking at the normal distribution. It's going to be quite a long video because we're going to be looking at everything to do with the normal distribution. We're going to be looking at how to use the inverse function, find probabilities, and standardizing. So first things first, what is a normal distribution? Well, it's an example of a continuous distribution. So you guys might have seen the binomial distribution video in an earlier series, and that was an example of a discrete distribution where the possible values of x can only be positive integers. For a continuous distribution, it means that x can be negative values first of all, and it can be any value. So it can be a rational number, it can be like a decimal number. This means there's actually an infinite many number of x values it can actually be. And so therefore we call it a continuous distribution. So for a normal distribution, you might have seen it in this kind of form here, where x is normally distributed with this mu, which stands for the mean, and this sigma squared, which stands for the variance. Okay, so these are the parameters for a normal distribution. And a normal distribution follows a bell-shaped curve. That's what we call this curve here, where this middle line is going to be our mean value. The mean value is just the value which is most likely to occur. That's why it looks like a highest probability. As we go further away from the mean value, then it's less likely to occur. So that's why it slopes down like in this shape here. Couple of characteristics we need to be aware of what this bell curve is. Well, the total area is going to be equal to 1 because we know that the probability, or the sum of all the probabilities has to be equal to 1, right? It can't be greater than 1. And secondly, it's symmetrical, meaning to the right of the mean value line and the left is symmetrical, i.e. that means this side is going to be equal to 0.5 and this side is going to be equal to 0.5 because the total area is equal to 1, right? And finally, because if we're asked to find x is equal to a certain value, it's going to be 0, right? Because the fact that there is an infinite many number of possibilities and the sum has to be equal to 1, we can't do 1 over infinity, so it's going to be equal to 0. So for a normal distribution, you'll be asked to find questions like probability that x is less than something, or the probability that x is greater than some other x, okay? If you are ever asked to find the probability of x is equal to, just automatically say 0. Right, so let's do an example. So let's say we have a normal distribution with a mean of 10 and a variance of 4. That means this middle line is going to be 10 like here, right? And I ask, what's the probability that x is going to be less than 12? Well, 12 is bigger than 10, so it's going to be to the right of this 10 line, so it's going to be roughly here. And what they're asking is basically to find this area like so, okay, which we can do later on using a calculator. If I ask them once again, what's the probability of x is greater than 8? Well, 8 is less than 10, so it's going to be to the left of the line, and it's greater than 8, so we're going to be asked to find the area to the right of this red line, so this area here. Now, the important thing about this is, right, 8 and 12 are both a distance of 2 away from the mean line here. So actually, the areas themselves are actually going to be the same. So the probabilities, if you were to find them, x is less than 12 and x is greater than 8, would actually be the same. Okay, so that's how we're using the characteristic of a symmetrical bell-shaped curve. Right, as I said, we can use a calculator to find these values. So if you have a Casio scientific calculator, then what you need to do is go to the menu button, distribution, and we're going to go for normal CD. We never want to use normal PD, okay? So just always use normal CD. And you'll see there's like a lower upper value, and then there's mu, sigma, values like this, right? So the lower means if we're trying to find less than, and upper means bigger than, okay? So we'll look at an example here. So let's do the same thing. We have mu is 10, sigma squared is 4. So I'm going to find probability that x is less than 12. So we're trying to find everything less than 12, right? So the upper value we're going to have to plug in is going to be 12. Now the lower one is going to be as small as possible. So ideally, in most cases, I recommend you going for minus 10,000. This should work in most cases. And then mu, obviously you go for 10. And now sigma squared is 4, right? So you have to be careful with this. So sigma is just the root of 4, so you have to plug in 2 rather than 4. And if you do this, you should get an answer of 0.8413, like this. Same thing for if I was asked to find the probability of x is greater than 8. Now we're trying to find 8 or larger, right? So 8 is now going to be our lower. Our larger now, I'm going to write a big number, so I'm going to write maybe 10,000 this time. Mu is still 10, sigma is still 2, and if you press equals, you should get the same value of minus 0.8413. So this is how we go about finding these probabilities. If I ask you to find what's the probability of x is equal to 8, well, we know for equal to, it's always going to be equal to 0. So now we can also find stuff like probability of it being greater than 8 and less than 12. Well, if it's greater than 8, it's going to be here, and less than 12 is going to be here. So we're basically asked to find this area here. So using the calculator, you can put lower as 8 and upper as 12, mu is 10 and sigma is 2, and you should get the value of 0.6826. Okay. But we can also do it without using a calculator because we need to understand how to manipulate this kind of stuff as well. So if I ask for the probability of it being bigger than 8 and less than 12, well, I can say I can find the probability of x is less than 12, which will be this whole area here. And if I minus this small area, this green area, then I'll get the area I want, right? So all I need to do is minus the green area. Now the green area, the way we would minus it, it would be, well, that's going to be actually 1 minus the probability that x is larger than 8, right? Because x being larger than 8 will represent this whole area here. And if I'm 1 minus it, I'll be left with the green area because the total area is 1. So therefore I can say, well, probability x is less than 12 we found earlier was going to be 0.8413 minus 1 minus probability x is greater than 8 was also 0.8413. And if you do this calculation, you should get 0.6826 as well. So you get the same value, it's just a matter of fact that we did some manipulation before. You need to be very comfortable with this kind of manipulation because later on we'll have to manipulate other kinds of probabilities. One more key point to note, if they ask you, for example, what's the probability that x is less than or equal to 12, or x is like bigger than or equal to 8, these are the same thing as x is less than 12 and x is greater than 8, okay? So if you don't get confused because there's just an equals to sign as well. Okay, let's try this question here. So we have the amount of mineral water W milliliters in a bottle produced by a certain manufacturer is modeled as having a normal distribution, mean 500, variance 14 squared. Find the probability that W is greater than 505. So it's greater than 505, so in a calculator we'll put low as 505, upper as 10,000, mean as 500, and variance or sigma as 14, not 14 squared, so just be careful of that. And you should get the 0.3605. For part 2, we're finding probability W is less than 490. Same thing for the calculator now. Now this time our upper is going to be 490, our lower is going to be minus 10,000, and same mu and sigma values. And you should get a value of 0.2375, like so. So it's just a matter of just practicing using the calculator. Right, a sample of 4 bottles is taken. Find the probability that all of the 4 bottles contain more than 490 millimeters. So we need to first find the probability that W is greater than 490, right, for each bottle. And this is the same thing as 1 minus the probability that W is less than 490, which we found in our part 2 here. So it's going to be 1 minus 0.2375. So this is the probability of one bottle having a water greater than 490, but they have a sample of 4 bottles and all 4 need to have more than 490. So we just raise this to the power of 4. And we should get 0.338 like this. Okay, let's try another question. So we have a diameter of bolts made by a particular machine modeled with a normal distribution, mean 13, variance 0.1 squared. Find the probability that a bolt chosen at random has a diameter less than 12.8. So they're asking us to find probability that D is less than 12.8, and you can just plug this into the calculator. We should get 0.0227. Right, B. Bolts are considered perfect if the diameter lies between 12.9 and 13.1. A random sample of 40 bolts is taken. Find the probability that more than 25 of the bolts are perfect. So this particular question is quite a common question in exam because we're actually having to use a normal distribution and then a binomial distribution in connection. So first things first, we need to identify the probability of being perfect. And they've defined what perfect bolt is going to be, and that's when the diameter is between 12.9 and 13.1. So first things first, we need to find this probability, and it's still following a normal distribution, so we can plug it into the calculator. This time lower will be 12.9, upper will be 13.1, mean is 13, and sigma is 0.1, and you should get a value of 0.6827. Now, so that's the probability of one bolt being perfect. Now they've said they've got 40 random bolts, and they were considering how many of them are perfect. So now it's actually turned into a binomial distribution, where the n value is 40, that's the number of bolts, right? And the probability of being perfect is the value we just got worked out earlier, so the 0.6827. And they're asking us what's the probability of more than 25 bolts being perfect. And so I can say this is 1 minus probability that x is less than or equal to 25. And this will be 1 minus 0.2655, giving us 0.7345, like this. So as you can see, we use the normal distribution to find the probability, which will then be used as the p-value for a binomial distribution. Right, so that was the normal distribution. We're now going to be looking at the inverse normal distribution. And what the inverse normal distribution is basically the opposite. So you're given a probability or an area value, and you're asked to find the recommended or the matching x position, okay? So let's say I have x is normally distributed. Let's go for the same thing, mean is 10, variance is 4. And so I've asked, what's the probability that x being less than a is equal to 0.6? So first things first, we need to identify where our a is. If this was 10, right, half the bet is 0.5, so a has to be to the right of it, which is 0.6, right? So a is going to have to be here, and this area they've given us as is 0.6, and they've asked us, what is this a value? Well, the way we do this is we can use the calculator. So if you go to the calculator, it's the same steps, but this time rather than buying normal CD, we're going to go for inverse normal, okay? And you should see that in the inverse normal column, there's like an area button, there's mu and sigma. The mu and sigmas are the same, so the mu would be 10, sigma would be 2, okay, that's the same thing. It's all about the area. Now for this calculator, it always asks for the area less than or equal to, okay, or just less than like this, okay. So in this case, it was the area less than a is 0.6, so you want to be putting in 0.6 in the area position. And you should get that a is going to be 10.5. Another example is if I ask you, what's the probability that x being bigger than b is going to be 0.2, okay. So first things first, we need to identify where b is relative to the mean. What is bigger than b is 0.2, right? So that means b is going to have to be also to the right, roughly here, where this area is going to be 0.2. To find this, you use the calculator again, the inverse function, and same mu, same sigma value, but for this area, you have to remember, the calculator always wants the area less than this x button, or in this case, b value. If the probability of being bigger than b is 0.2, the probability of being bigger than less than b will be 0.8. So for the area, you need to put in 0.8. Okay, so to be very careful with this. But if you do that, you get the b value is going to be 11.7. So this is what the inverse normal function of the calculator does for us. Right, so let's try this question here. So with the random variable x, normally distributed, mean 80, variance 16. Find the value of a and b such that the probability of x being greater than a is going to be 0.4. So once again, use a calculator, you're going to be putting in mean is 80, sigma is 4, okay, remember it's square root of 16. And for the area, remember, we want to find a less than, so if the bigger than is here, if this is 0.4, it means less than a will be 0.6 for the area. So for the area, it needs to be between 0.6, okay? And so if you do that, a you should get as 81.0. Right, part 2. Probability that x is less than b is going to be 0.5363. They've already written as x is less than b, right? So for the area, we can just plug in 0.5363, so we don't really change it, and get the value for b, which comes out to be 80.6, like so. And for b, they're asking us find the probability of being between b and a, so larger than 80.6 and smaller than 81. Okay. Once again, now you can just use a normal CD function. Lower will be 80.6, upper will be 81, and the same mean and variance value. And hopefully you should get a value of 0.0364. Okay, let's try this one here. So we have the percentage scores of a group of learner drivers in a theory test is modeled as a normal distribution, mean 72, variance 6 squared. Find the probability of a such that the probability of x being less than a is 0.6. This one we've done a lot before, so just this time we have to change the area because x is less than a already. So the area would be 0.6, which you have to plug in to get that a comes out to be 73.5. Right, part B, find the interquartile range of the scores. Right, so the interquartile range, if you remember, is just the difference between Q3, the upper quartile, and Q1, the lower quartile. So we just need to find Q3 and Q1 separately. Now we should remember or understand, I've learned already, that Q1 represents 25% of the data being less than that value, right? So if this is Q1, then this area we can say is going to be equal to 0.25. Same thing for Q3. Q3 represented the value at which 75% of the data was less than it. So Q3 would be roughly here, and therefore anything less than Q3 would be this 0.75 like this. Knowing this, we can create some probabilities. So I can say that the probability that x is less than Q1 has to be equal to 0.25, and the probability that x is less than Q3 has to be equal to 0.75. This is how we form our own equations, which I can now plug into the calculator, and Q1 you should get 67.95, and Q3 is equal to 76. And the interquartile range will just be the difference between the two values, okay, which is So it's easy to calculate. Right, so as you can see, for a normal distribution, there are many different possibilities of mu and sigma. There can be any combination of these two. But there's actually something called a standard normal distribution. And that's when it's got a special letter, we call it Z, and it's normally distributed with a mean of 0 and variance of 1. So this is a standard one. This is useful for us because it allows us to create further equations linking different distributions, different normal distributions together. And the way we link them or make them into a standard normal distribution is by using this code here. So this is the code of changing any other normal distribution into a standard normal distribution. And the code is x minus mu over sigma. In the formula book, you might see this normal table here. It's sometimes called a percentage table, okay? And this tells us the property of z being larger than or equal to some z value. And it only is applicable for a standard normal distribution, i.e. when the mean is 0 and the variance is 1. So you can't use these values at all when you're using other normal distributions with other mean and variance values. But once we have standardized it, then we can use these values for later on to create further equations. Okay, so let's look at this question here. So we have this here, and it's, as you can see, it's z, meaning that z is normally distributed with mean of 0, and variance of 1. And so for part A, they're asking what's the probability of z being less than a is 0.9082. For this one, you can just plug it into the calculator again. Mean will be 0, variance will be 1, or sigma will be just 1, and then a you should get as 1.33. Right, for B, they're asking us what's the probability of z being larger than a is equal to 0.0314. Once again, this you can plug into the calculator, but remember to change it to less than, right? So this is going to be, probability that z is less than a is going to be 1 minus 0.0314, which we can then plug into that calculator as the area. Right, for C, C is asking us what the probability of z being larger than a is 0.15, okay? You could use the calculator, change the area to 1 minus 0.15, which is 0.85, and plug it into the calculator, or you can use this table here, because this table, remember, shows us that z is larger than or equal to z. So it's already in the form z is bigger than a, right? So that's 0.15. So we need to find the p-values. Out of it, we need to find the p-value, which is 0.15, which is going to be this one here, which means that the z value for this, or in this case our a value, is going to be 1.0364. That's how we use this percentage table table for a standard normal distribution. Let's carry on. So for D, we have probability that z is larger than a is equal to 0.95. Once again, I can plug into calculator. I can change 0.95 to 0.05. This is less than, and plug into calculator. But I can also use this table. Right, so if it being bigger than a is 0.95, we know that a has to be here, right? Because it's to the left and then one side is 0.5. So a is going to be here, where this area is going to be 0.95. But what I can do now is I can create another point here, b, and I can say that probability of z being less than b is going to be also 0.95. Okay, if they're symmetrical, I'm going to say that they're symmetrical. And so if I say probability that z is larger than b, it's therefore going to be 0.05 like this. Meaning that B, I can look for 0.05, which is going to be this value here, 1.6449. And I'm assuming that the distance between B and the mean and A and the mean are the same, okay? Therefore, this A value would therefore be, this is on the negative side, negative 1.6449 like this. So we're just using the fact, or just manipulating these probabilities so that we can use this table here. But one thing, as I said, you can also use a calculator if you find that a bit more easy. Let's try part E. So probability of being between 0 and A is 0.3554. So the probability of being between 0 and A is 0.3554. Now this is for Z, right? So meaning that the mean value, i.e. the middle value, is going to be 0 point here. So this is going to be A, so this is 0. So they're saying that this area is 0.3554, meaning that anything less than A, this is less than A, will therefore be this half area plus this area, and this side, each half is 0.5, right? So we have to find 0.8554, which I can plug into the calculator to find my A value. And let's just try one more. Let's just try G. So between minus A and A is 0.8. So the probability that Z is between minus A and A is going to be 0.8. Once again, let's draw our bell curve. It's good to visualize it. So if I draw like here, if A is here, if minus A is here, then A is going to be here, right? And therefore this area is going to be equal to 0.8. So therefore, if I say, what's the probability of Z being less than A? Well, that's going to be this total area, right? And we know that the total area has to be equal to 1, meaning that these small sides either side is going to be 0.1 like this. So Z being less than A is going to be actually 0.9, 0.8 plus 0.1, right? And the probability of Z being larger than A will therefore be 0.1. So I can use the calculator and put in the area as 0.9, or I can use this table and find 0.1 like here to find the value of our A value. Right, so as I said, using the code we can create further equations to find mu and sigma. So we have a random variable x, which is normally distributed with mu and sigma squared. So they haven't given us a mu or a sigma squared. Instead, they've given us what our lower quartile is, which is 25, and the upper quartile, which is 45. So I can say that the probability that x being less than 25, which is the lower quartile, is 0.25, and the probability that x being larger than 45, which is the upper quartile, less than 45, is going to be equal to 0.75. So with these two probabilities, we can actually find our mu and sigma, and the way we're going to do that is standardize it to z. So I can say that probability that, remember this code was z is equal to x minus mu over sigma, right? This is a code of standardizing it. So I can say x will not change to z, less than, our x is 25, so it's going to be 25 minus the mu value, which we don't know, over sigma is equal to 0.25. I can do the same thing with the second inequality, so I can say that probability of z is less than x is 45 minus the mu, which we don't know, over the sigma, which we also don't know, is equal to 0.75. And from here, I can use the inverse normal, because the area is 0.25 and 0.75. I can say that, so 25 minus mu over sigma is going to be equal to minus 0.6745, and 45 minus mu over sigma is going to be equal to positive 0.6745, like this. Meaning that I can just create two equations. So this is going to be minus 0.6745 sigma, and 45 plus mu is going to be equal to positive 0.6745 sigma. I have two equations, two unknowns, so I can do simultaneous equations, giving me that mu is 35 and sigma is going to be equal to 14.8. So we use the code to change it into a normal distribution or standard normal distribution to create further equations, and then we use the inverse normal function to create or find what our z value is. Okay, let's just try this final one here. So the masses of a penguin on an island are found to be normally distributed with mean mu and standard deviation sigma. So let's say penguins have a normal distribution of mu and sigma squared, which we don't know. Now, given that 10% of the penguins have a mass less than 18 kilograms, so the probability of P being less than 18 is 10%, so that's going to be 0.1. And 5% of the penguins have a mass greater than 30, so the probability of P being greater than 30 kilograms is going to be 0.05, i.e. 5%. Sketch a diagram to represent this information. So if I was to sketch a diagram, like here, then we can say that less than 18 is 0.1, so it has to be on the left-hand side. 18 is going to be here. This is going to be 0.1. Larger than 30 is 0.05, so 30 is going to be right-hand side, and this is going to be 0.05, like this. B is asking us to find the value of mu and sigma, so what we're going to do is now standardize it like we did before. So I can say that the probability of, remember z is x minus mu over sigma. So the probability of now z is less than 18 minus mu over sigma, and that's still equal to 0.1. The second one will be probability of z being larger than 30 minus mu over sigma, and that's going to be equal to 0.05, like so. Which I can now use the inverse normal function to give me that 18 minus mu over sigma is going to be equal to minus 1.282, and 30 minus mu over sigma is going to be equal to 1.649. Make sure when you're doing this, finding this z value, you have to put in the area 0.95, right? Because this is larger than, and we want to change it to less than. But once we've done this, now we can, once again, like the previous example, we've got two equations, and I can do simultaneous equations or substitution to find my mu value, which turns out to be 23.3, and sigma is going to give you 4.1, like this. Okay, so as you can see, these two past examples, we're just using the code to find us the mu and sigma values. So this is basically all the basic information you need to know about the normal distribution. Just practice some more exam type questions, and if you guys still have any questions, just leave some comments down below.